sorry for rushing through this a little bit. In fact, you can learn much more about Bayesian networks and Bayesian reasoning here at HSE than I could tell you, because I'm not the expert. I was rushing a little bit because I wanted to get to the next main point, and I really wanted to have more time for that. So let me slow down a little bit and let me talk in more detail about what I came here to tell you about, and that is prediction. So far we've modeled everything, but we don't know yet how to make predictions, right? We only know how to estimate probabilities. So what we did so far is we have a graphical representation, network, etc., etc. That's our choice. Then we looked at how do we estimate these values. We saw it for Bayesian networks. We will see it likely tomorrow for Markov networks, which we can learn the actual distribution then based on data. But then we're not done. Then we have a model. So what? Now we want to use this for prediction. We want to be able to learn a function that given an image predicts a pose, that given an English sentence predicts a French sentence. So like a function that takes any kind of input and output some interesting thing in return. So that was what I motivated the whole thing to start with. And now we'll finally get how to do that. So first question is, if we want to do this for structured data, what distribution should we use? We know how to model the joint distribution of inputs, outputs. We would call it P of X and Y. We would know how to model inputs given outputs. We would know how to model outputs given inputs. What should we use? And second, if we know which distribution we're going to use, how do we actually now predict some kind of Y given an X? So which one should we predict? Out of this whole distribution of all possible values, which one? So of course, we don't want to predict a random value. We want to predict the best possible outcome. And for that, we have to think about what does it mean to make a decision and what does it mean to make the best possible decision. And that is the excursion into decision theory that most of you should have seen if you took a course in like pattern recognition or something with classification. But I'm going to go through it anyway. Typically, what you look about is, let's solve a classification task. So what you want is you want to take images X or any kind of objects X, and you want to assign them a label from a set Y. For example, here, is it an A or B? And for the moment, assume that we are given the probability distribution. We are given the true distribution of X's and Y's. Now, how do we decide for any kind of fixed X? So this is a classification problem. And we can ask ourselves, well, what mistakes can we make and how do we avoid them? So let's introduce a function that for any input outputs an output, a function that classifies an object into one of the categories. We call it the decision rule. And then we can measure its error as the generalization error of the prediction rule is the probability that it makes a wrong decision, right? So what does that mean? For any fixed X, you can evaluate your prediction that gives you a Y, and you can compare that to the true Y that this object really had. So, and then you can compute the probability of this being not the same. So you compute the probability over all the XYs from the distribution that you know, that the output of my decision rule differs from the correct label. So for any possible combination, how likely is it that I'm wrong? If we take the probability of that, we call it the risk or generalization error of our decision rule. Clearly, we want a small value. If the probability of making a mistake is small, that's better than if the probability of making a mistake is large. So, given that we accept small values of this generalization error as the quantity we care about, so we want to really minimize the number of wrong decisions, then it's actually not hard anymore to write down the best possible decision rule. It's called the Bayes classifier. So the prediction rule, it minimizes the Bayes, the generalization error, so it has the smallest of all possible errors, is the simple rule. Well, it's the minimizer of the risk, that's not the rule yet. So how does it look like? Well, you can compute for every possible input, you can compute the output of the rule as look at the conditional distribution of all possible outputs given the input x, and then take the y that has the highest probability. So this is similar to the maximum likelihood, right? Only now we're not reasoning about parameters, we're reasoning about objects. And in fact, since this is the conditional distribution of the y's given the x, it's also called the maximum posterior distribution rule map. So why does this make sense? Let's go through it in short steps. So what do we really want? We want to find a rule that makes as few wrong decisions as possible. So it should minimize the risk, and the risk is the probability of my decision is different from the real label. And we can also write that for, so this is the distribution, the probability over x's and y's. So we can split this over as a probability over all x's, and then for each fixed x, we are still uncertain about the y. So we can decompose this joint thing into the expectation over all possible values, the probability that just for this value, the prediction is different from the one given by the distribution of all outputs that are correct for inputs. So the thing we want to minimize is the expectation over x of some probability of mistake for a fixed x. Now we put no constraints on what our classifier is allowed to do. It can choose a completely different value for every different input, right? It's just a function from x to y. So that means in order to make this probability of mistake small, well, we can just make the probability of mistake for every x separately small. If for every single x we have the smallest possible error probability, we also have the best error probability across all possible x's. So let's just try to minimize for every fixed x the probability of making a mistake. So that means we should choose the probability, the output of our classifier for any fixed x should be the output y that has the smallest probability of being different from the label that this thing really has under the distribution p of y given x, which is the true distribution of our data. If this y given x is confusing to you, that is because for some things you do not know, there is not just one single outcome that can happen. If you roll a die, it's not that there is just one outcome. So if you don't like this kind of, well, there is uncertainty in the true y, think of this as a delta peak at one location. So if just one output is possible, that would just be the probability of not predicting that value. So the probability of predicting something else than what the output really should have been is the same as when we minimizing that probability is the same as maximizing the probability of predicting the right thing. And the probability of predicting or maximizing the probability of something under the distribution of something happening. Oh, this is horrible. Okay, so maximizing the probability of predicting something else than the y is just, we choose the element that has the highest value here. So it's exactly the one that has the highest probability. That's the maxima, the label y that has the highest probability on the model. This is harder to write down than to think. If you don't want many mistakes, choose the most likely answer. So predict the value of maximum probability. So this is the maximum posterior prediction, where the posterior is the y given the x. So what do we have to do? Look at your distribution. For every fixed x, how likely is each y? Choose the y that is most likely. So is this the right thing to use for every situation? Should we always predict with this classifier? I mean, we know that it minimizes the number of wrong decisions. So typically that's a good idea. But sometimes it's not. So when is it not a good idea? Well, when the number of mistakes is not what you're really after. So there's a situation where different kind of mistakes have different consequences. So there's a classic example of a doctor who has to decide whether a patient has cancer or not. So he looks at the x-ray, there's a little shadow, but with 80% it's harmless. What would you diagnose? If you want to minimize the probability of an error, you would say there's nothing because you're 80% certain there's nothing and just 20% certain that there's something. So 80 is more likely than 20. So more likely say there's nothing. But what would be the consequences of doing that? So there's 4 possible cases, right? So either the patient has cancer and the doctor says cancer. That's good. Well, it's not good, but it's the best under the circumstances. Or the patient has no cancer and the diagnosis is no cancer. That is actually good. And then there's the 2 cases where the doctor made a mistake. So if the patient has no cancer but your diagnosis is cancer, that means, well, the doctor will be sent to a specialist. There will be extra tests. That is an inconvenience. It's not good. So there is some kind of negative consequences. But the opposite case, when the patient did have cancer and your diagnosis was no cancer, is much worse. Because then the patient will go home, feel happy, the cancer keeps growing, and the patient might die. So erring in one direction is much worse than erring in the other directions. And this is a common thing it's a situation that happens more often than not. So often one kind of mistake is much worse than the other kind of mistake. And then the Bayes classifier will not be the perfect thing to do. So in order to reason about this formally and come up with a different rule of decision, we have to assign values to these outcomes, and that is done by introducing a loss function. So we will need a function that tells us how bad is every decision, how bad is every mistake. So it's a function that takes 2 arguments. Both of them are labels. And one of them will be the correct outcome, and one will be the outcome that you actually produce. And then the loss L of y and y bar will be, well, how bad is that to happen? So if the correct answer would have been y bar, the correct answer would be y, the first argument, but instead I predict y bar, which is the second argument. What happens? So for the doctor argument, you can just write that down schematically. So if you predict the right thing, well, loss is 0, you're a good doctor. If you predict the right thing, it's still the right thing. If you predict cancer, even though there was no cancer, then there is a loss because there is some negative consequences of that. But if you predict it the other way around, correct would have been cancer, you predict no cancer, then it's a much larger number. So I just put 1,000 because 1,000 is a big number. But if you go to the doctor's insurance companies, they actually can put a number in terms of dollars there. So if you want to be insured, you're insured against malpractice, and they know exactly how much it will cost you if you tell a patient he has not cancer, even though he has cancer. So you can think of this even as money, if that is what you like. Okay, so now what is a smart, rational strategy for a doctor to do? Well, you should not decide based on making mistakes, but on getting as little penalty in expectation as possible. So having as little bad consequences as possible. So that means you have to minimize the expected loss that you will suffer. So if I make the decision y, but the correct the correct value would have been y bar for my input x, then this will cost me something. So this is the cost of saying y under the distribution that the correct label would be y bar. If we do this for the doctor, well, there is 2 cases. If you say cancer, then there's a certain probability that this is correct. In that case, you have 0 loss, and there's a certain probability that you have that your decision is incorrect, and then you will have a loss of 1 because you said cancer even though there wasn't any, and in expectation, your loss is 0.8. In the case where you say no cancer, there's a certain probability that we're correct. It's actually a large probability. In 80% of cases, you were correct. But there's also a 20% chance that you were incorrect. In the incorrect case, loss you suffer is much higher. It's the loss of saying no cancer, even though there was cancer. And then your expected loss of this decision is much, much higher than in the other one. So in the end, you would rather say cancer than no cancer, just to be on the safe side. And only if you're really, really more than 99.99% certain that it's not, you would say not. And I would expect that, but that's why people get sent to specialists so often. It's a good thing, right? Okay. So as we defined the generalization error as the expected number of mistakes, you can define the error as the risk of a decision as the expected loss. So what's in expectation over all my data is going to happen to me in terms of being wrong measured by my loss function. So this will be the expected value of predicting, the classifier predicts c of x, the correct value would have been y, we measure the loss between them, and that gives us a measure how bad or how good did the classifier C do in expectation over all data. And then we know which classifier is the one that works best under this measure of quality. It's the one that for every individual x chooses the loss, the answer y that has the smallest expected risk. So for the doctor, that was the cancer option instead of the non-cancer option. Okay. The first case of errors is a special case of the second. So if your loss function is the so-called 0-1 loss, so it just checks if the decisions are the same or not the same, then you will get back to the original thing. And in fact, I mean, I explained it with the same or not, but you can also define these loss functions with respect to continuous quantities. So for example, if you want to measure the distance to something which is a continuous quantity, your loss function could be like, well, the absolute value between the value you predict and the value it really was, or the squared distance between them, and so on. So all these quantities are nice, I mean, work for continuous predictions as well. Okay, so now we know that in order to make predictions perfectly, we need a loss. We need to know what do we actually want. So if we want to predict structured objects, we need structured loss functions. And here's a few examples. First of all, it's obvious that a loss function, which for some magic reason now called delta instead of L, a loss function would still be a function of two arguments. It will be the predictions you make, which is now a difficult structured object, and the correct prediction, which you don't know, which is also a difficult structured object. So it will always be a function of two arguments. But what you actually compute will depend heavily on what kind of prediction task you want to solve. So if you want to predict secondary structure of RNA, you will need a different quality measure between the correct structure and the structure you predicted than if your goal was to do pose estimation, right? Or if you wanted to segment an image or want to parse a sentence and so on. So this is really, the loss function is really something that you cannot, I mean, you must have a domain expert that tells you this is a good prediction, this is a bad prediction. I personally would not know if this is a good prediction of the RNA structure or not. Even if you show me one and you show me the other, I don't know how to compare, so it's domain knowledge. But there's a few general patterns that occur. So the first thing you can think of is let's just check if we are right or not. Right? So this is the 0-1 loss we saw before. The prediction is y. Your correct answer would have been y bar. Are we the same or not? And if we are the same, we get 0 loss, and if we are different, we get loss of 1 or any other constant you want. That means every mistake you make is equally bad. For structured prediction problems where you predict many things and they have like parts that interact, that is rarely a good loss to use for actually measuring performance. It will be very hard or very rare that you predict every single thing in your structured model perfectly. Typically, I don't know, if you do image segmentation, there will be at least 1 pixel maybe off, right? You don't want that a segmentation with 1 pixel different is as bad as a prediction with all pixels wrong. Right? So 0-1 loss is typically not the best thing to use in these cases. Often a better choice is so-called Hamming loss. So if you have a prediction that consists of multiple interacting parts, you can check for each part separately if you predicted the right thing or not. So in this sentence example, if you want to do part of speech tagging, you have a sentence and then you predict an output, happens to be this one. The true output would have been this one. So then you check for each individual location, did you predict the right thing or did you predict the wrong thing? 4 times the right thing, once the wrong thing. If you average that over all locations, you get a loss of 0.2. And clearly, if you assign wrong things everywhere, you get a higher value than if you just make a mistake at one location. So this is actually often used quite often in practice if you have this kind of nice decomposing structure in your problem. If your quantities are continuous that you predict, then checking for equality will not do the job, right? You will never be spot on exactly right. So then you would rather use something which is like a numeric quantity for each location. You would still decompose your problem into subunits, so each word or each body part. But now instead of checking yes or no for each part, you would put a different criterion there. For example, the difference of 2 vectors or for the body parts, is the rotation correct? It would also be a numeric quantity that you can compute, and so on. So this is very common in many geometric problems where you try to predict like location of some articulate object. You can look at each part separately. And finally, there's a lot of application areas which are just very specific for the individual problem. So for example, for object boxes, so if you have an image and you want to find where is the object that I care about, like where is this chair, the correct location is over there, it's maybe a box of that size, but I predict a box over here. How do I measure if this was a good or not prediction? Well, there is specialized losses for many of these cases. So for the bounding boxes, it would be, for example, the intersection over union loss. So you look at the area of the intersection between the correct prediction and your prediction, and then you divide that by the area of the union of the two. So the union will always be bigger or equal. So you will get a number between 0 and 1. And so it's 0 if the prediction and the correct don't overlap at all, then the intersection is 0. Right? And if you do 1 minus that, you will have a loss that is large if you predicted exactly the right thing. No, it's 0 if you predict exactly the right thing. It's large if you predicted something that is completely opposite from what you wanted. And it has some nice properties. For example, it's scale invariant. So if your boxes are twice as big and your prediction is also twice as big and shifted, this would cancel out. So it's not that you get large losses for large objects and small losses for small objects and so on. But it's one of these examples which are really different for different tasks. Yes.
What about size of detection and ground squares?
Mm-hmm.
Can detection be bigger
yes.
than green square? And
yes, it is.
Can contain it, but
yes.
not true.
No, it can. I mean, if you predict the... So yes, what happens if you have a really large prediction but a small ground truth, or vice versa?
Yes, well, like black.
Okay, yes. So this is that the prediction or the ground truth? Is that the true or the...
But yes.
Okay, so if this is the true answer, and I predict something smaller, then the intersection is just a small area, the union is the big area, so I would get penalized by the ratio of sizes. And vice versa, if the true answer is the small one, but the prediction is the big one, it would be the same thing because the intersection is still the small one and the union is still the big one. So if one is a subset of the other, it will always be small divided by big, so it will always give you something. It's a well-designed loss. It's horrible to use numerically because it's not differentiable and so on. But I mean, no, it's indifferentiable, but it's not. Well, never mind. Okay, so that at least gives us a very clear criterion how, if we have a distribution of all the things we care about, how we should make predictions, right? So we are given a distribution, maybe our model distribution. Then we should pick the prediction for an input x that minimizes the expected loss, right? So for any fixed x, choose the output y that has the smallest expected value under the conditional distribution of the outputs given the inputs. So if you do it continuously, you need to compute the probability of every possible output under the input multiplied with the loss, and then check the one that has the smallest sum of this size. If you think of what is this y space, this big summation, that is the sum over all possible outputs. So it's the all possible configurations of the variables we care about. If you have 1,000 random variables, each of them with 2 states, then this curly y has 2 to the 1,000 elements. I don't know how many that is, but a lot. So you do not want to really sum over these things explicitly. Right? So this is the rule in order to optimally predict, but not always can you actually compute this decision, especially not efficiently. There's a few exceptions though. And one of the exceptions is the 0-1 loss that I started with. I said it's not a good idea, and it's not. But at least if you want to find the assignment that is the optimal one under this loss, you don't have to sum over everything. You would only have to find the one configuration that has the highest probability. And there's efficient algorithms for that often, and we're going to talk about them tomorrow. The other alternative is this Hamming loss. So that was a sum over all the individual parts of your model, and you check for each one of them if it's correct or not. You can check that this will turn into 1 minus the sum over all the parts, so the variables that you're reasoning about, of the probability of that thing. And I mean, all of these are conditioned on x, that. And that in order to minimize this risk, you have to maximize this guy, and it's a sum over many things, so you can maximize each term of this sum separately. And then that means you can decide about each element of your best solution separately based on the probability of, well, the probability of just this random variable having a certain state. All the others are marginalized away. And if you can do so-called marginal inferences, which is what we're going to talk about next, then you can also compute these things, and you can also do optimal decision for Hamming loss. For the next one, I had the squared loss. It also sometimes works for the intersection of a union or some other specific losses. Typically, there's no hope in getting the optimal answer under this. It's just completely intractable. Okay, so this closes the first part of my lecture. Turned out it was almost 2 days. It's about how to come up with a model, how to fill the model with values based on data, at least some of it, and how to make decisions once you are given that. None of that is concrete enough that you would actually do it in practice yet, but the concepts should be there. The next part of the course will be about algorithmic things. So how can we actually do these things in a computer? So how do we actually compute these marginal probabilities given a huge model without having to sum over the exponentially many things that are in between? Okay. Are there any burning questions? Now is a good time. Really? Monday you were asking like crazy. Today nothing. What happened? Are you lost? Is it too fast? Is it too slow? Is it too exciting? Too boring? Okay, you can tell me afterwards or in an email. I mean, from an anonymous address. Okay. So what I'm going to talk about is one of the big, actual research areas in graphical models, and that is probabilistic inference. And if you sum it into a few symbols, it would be compute the probability of a few variables given others. The others is not the problem. The problem is that it's just a few. It's not the probability of everything, it's just the probability of a small subset. Mathematically, we know that there's no problem, right? We just marginalize out the others, we are done. But in practice, marginalizing means summing over all configurations, and summing over all configurations might be completely impossible in practice if there's 2 to the 999 of them. So if we want to use this method, these models in practice, it's not enough to have the mathematical definition. We also need the algorithms to do these operations that I've defined mathematically. And the first thing we can think of is giving you an overview. So we're going to talk about inference in graphical models. You might have heard about belief propagation. That's the first thing we're going to talk about. And then these are exact methods that give you exactly the right probabilities. Turns out for many models you cannot compute the stuff exactly, but you can at least compute it approximately. So then most likely on Friday I will talk about loopy belief propagation, MCMC sampling, variational inference, and if I have time, deep networks. And that will be followed by part 3, part 4, and part 5 of my lecture, all on Friday. Okay, belief propagation. Let's take a model, a simple example. We have 4 variables, y1 to 4. We arrange them in a nice, horizontal line. And it's a factor graph, so we know exactly what the distribution will look like. It will be a product of 3 terms. Each of them will have 2 input variables. That should be clear, right? So we have one big random variable that consists of 4 parts, and we say, and each of these parts can take values in a set that we put with the curly y with the index of the variable. So yi takes value in curly iy, and so on. So the number of states that this had is, well, it's the product of the individual states. Okay. So now what we want is, for any fixed y, can we compute the probability of that y? So for any configuration of, assignments of these 4 variables, can we compute its probability? And in fact, you can forget that I put an x here because I didn't put an x here at all. Just forget the x for now. So we are given this model which has 4 components. It has some tables, it has some values. Can we actually compute the probability of one of the elements? That shouldn't be so hard, right? After all, this is a model of our probability, so it shouldn't be so hard to actually compute the probability of some configuration. So the probability model we have is, we know it's the exponential of some energy function. The energy function decomposes into 3 terms, according to this graph. And we have a normalizing constant in front. Again, just forget about the x. The only problem with that is we don't know what the z is, right? We can easily evaluate the function e itself. It's these 3 functions we know. We sum them up for given values of y. No problem. We get the exponent. We still don't know what the probability is because we don't know what the normalizing constant is. So let's compute the normalizing constant, right? What is the normalizing constant? Well, it's defined in a way such that when you sum this guy over all possible y's, it will turn it will sum up to 1. So we saw that the partition function is the sum over all possible values of y of the unnormalized thing here. Now here comes the problem. Making this sum over all possible configuration of all variables that grows exponentially in the number of variables we have. Here, the number of terms that the sum will have is the number of possibilities for the first variables times the number of the possibilities for the second, times number of the third, times number of the fourth, and so on. So if each of these has 1,000 possible values, that is already a trillion or so? I don't know. It's a large number. We don't want to do that. And in fact, a large part of graphical model research has been invested. How do we compute this partition function efficiently, or how can we avoid computing it in the first place? So how could we do that? Finally, we drop the dependence on x. So what we have to do is we want to compute this sum over this exponential of all the possible evaluations of our y. What can we do? Okay, first of all, we can plug in what we know, right? Every time you have a math question, the first thing is you check what are the assumptions and you have to insert them somewhere. If you don't use them, you didn't find the right answer. So let's put in what we know. For convenience, let's expand the sum into the 4 individual sums, and the energy has the 4 the 4 random variables as input. Now what do we know? We know that this energy is not arbitrary, right? It's the sum of 3 terms that correspond to the logarithm of the factors, and it decomposes according to this graph, right? There's one term that looks only at these 2 variables, one term that looks only at these 2, and one term that looks only at these 2. So let's call them f, g, and h. So we have one term here that looks at the first 2, one for the second 2, one for the third 2. Okay. Now does somebody see what we do? There. Okay, I'll do it. I move it up. Now? Anyone?
We represent them as a product of values, and then we try to move them to the left.
Exactly.
Not to sum over all of them, but to sum over only some.
Exactly. So first of all, we take the exponential and we write it as a product because the exponential of a sum is the product of the terms. So it's exponential of the first thing, exponential of the second thing, exponential of the third thing. And now you see that something happens. So this is a sum over all states of YL of a product, but this term doesn't even contain YL. This is just a constant with respect to the 4th variable. So we can take this thingy and we can move it out of the summation to a different location to here, but it also doesn't depend on yk, so we can even move it here, right? This guy doesn't depend on yl either. This is also just a constant with respect to yl. We can move it to that location, right? So what we end up with is we have distributed our terms around a little bit. Why does that help us? Well, now we can check what kind of work we still have to do. This is the same expression. I just move it up. What is this guy? You have, for all configurations of k and l, you get a value, right? So this is a matrix of the same size, number of possibilities times number of possibilities. And now what you do is, for each possible value of k, you sum it over L. So that means for every possible value of k, you sum this matrix over its, rows. And what you get is one number for each k. For each possible value of yk. Is that clear? So if you fix yk to a certain value, you can actually execute this summation over yl in each case, and every time what comes out is, well, it depends on yk, so it's one number for yk, and I call this, for specific reasons, some complex some value of only yk matters. So we did we constructed a matrix, we summed it over its rows, that gave us a vector, and now we have the entries of the vector at that location. So far we invested, well, number of states times number of states in order to compute this vector. Now what's next? Well, we look at the next one, moving it up. What is this? For every fixed value of yj, this guy depends on yj, right? So for every fixed value of yj, what is this? It's a matrix as big as number of states times number of states. And then we sum it over its rows multiplied with another value that depends on the summation index. This is just a matrix vector multiplication. It's something two-dimensional, something one-dimensional, summing over the one dimension. The result will be a vector again, which I call this complex thing of whatever value of yj we put in. So this is a matrix vector multiplication. And now you see the pattern. We come to the next sum. What is this? Well, for every possible value of yi, this is a matrix vector multiplication again. So we get a vector out of it, and then we can have to still sum the vector over all of its components. And if we do that, we have computed, so we name it that. Now we have to sum that one, that is this, the sum over a vector. So what we have achieved in the end is we have computed this thing over number of states to the fourth as a sequence of number of matrix vector multiplication, which are number of states squared. Okay? So we have found a more efficient way of computing this quantity by just shuffling terms around and checking what depends on what. And graphically what happened, and I didn't talk about that yet, is you think about each of these variables in the chain, you collapse them into some kind of smaller unit, and you pass it on to the next. So what we did here was we took the last element, which corresponds, for any fixed value here, we took these guys and we merged them into a new quantity, and then we passed it to that point. And afterwards, we didn't have to take care of that anymore. It was already summed away. But we had some additional thing to take into account here. Now we did the same here. For every fixed value of that guy, we collapsed these two into one vector. Oops, there it is. And now for x, and that one, we didn't need that one anymore. And so on, we passed for the left until we ended up at the beginning, and then we just sum all the values and we have our partition function. That works for chains, where you start on the right, you sort your stuff, and you go to the left. It also works for trees. So what you have to do is you have to pick a root node. Let's pick this one. And then you start at the leaves and you do the same trick. So this is a leaf. This is a leaf. If we want to compute our partition function, we take our big sum, which now has 5 different summations. We have an energy function of which we know that it decomposes into terms which always look at 2 variables at a time, right? We spread it all out. What we end up with is one term. So for a fixed value of yk, this guy depends only on yk, and we have to sum over all its states. So this is exactly the same as before. It's like the end of a chain argument again. This thing will collapse into one vector. Here the same. For every fixed value of yk, we can sum over all configurations here, and this thing will also collapse into a vector. Now this guy has two neighbors instead of just one, so what we'll end up with is two of these vectors next to each other, but that doesn't stop us. We only have to multiply them in a component-wise way. We have something two-dimensional, something one-dimensional, summing over all state. This is still a matrix vector multiplication. It turns into one vector. This vector has to be multiplied with another matrix. And as in the case of the chain, we start at the leaves and we execute the summations such that we don't have to look at these variables anymore for the rest. So we got rid of the leaves, now we get rid of the next ones, and so on until we reach the root node. So this is the so-called belief propagation or sum product algorithm. Since we talk about factor graphs, there's actually a very easy way of writing this thing. And it takes a bit, actually it's much harder to explain than to implement, I have to say. But it takes some getting used to thinking in terms of these, what do we collapse and where do we send it? So actually doing it in practice needs some, if you execute it for a 3x3 chain, you get actually some use after a while. But if we do this on a factor graph, we have a very efficient way of characterizing the operations we have to do. There's just two different operations that can happen in a factor graph. And that is, we take our previous view where we send a message from one variable to the other. So instead, we're going to think about two different ways. We're going to send messages from variables to factors, so from round little nodes to black nodes. And then we're going to pass on from the black nodes to the next variable again. And each of these steps has a very simple rule. If you want to send a message from a variable to a factor, that just means you take all the neighbors of that variable that are not the same factor, and you multiply their messages. So if you have a factor that is connected to two things, well, one of them, you want to send a message to f. This is the variable, this is the factor. So to send a message to f, you check all the neighbors of this, you take their vectors, multiply them together, and that is the message that f gets. So the message from y to f is the product over all the incoming messages to y from factors that are not f, multiplied up. You can imagine that if you program this, it's, well, multiply a couple of vectors, you just need to find out which indices they have. The second thing you might want to, you have to do is then you pass on this message from the factor to another variable, and that is this matrix multiplication we saw before. So you take all the incoming messages, so that is all the messages that correspond to a neighbor of your factor that is not the variable where you actually send your thing. So if you want to send something from f to yi, you take all the neighbors of f. Well, it just has two neighbors. One of them is yi itself. So you only need to take the message that comes from the other variable. That's this one. Then this factor is a function of two arguments, right? That's how we constructed it. Every factor has two arguments, which is the two variables it's connected to. So that is the matrix. And then we sum over all possible states of the first one. So this is just the matrix vector multiplication. And
normal red line goes from y to f, and in the index of f, it goes from f to y.
That is stupid, you're right. I think these should be flipped, yes. I mean, the notation explicitly says send a message from f to y, so yes, the error should be flipped. Sorry about that. I copied this, I stole this slide from somebody else, it's his fault. But yes, I'll tell him. Okay, yes, sorry about that, I'll fix it. Okay, so with these two operations, all you need to do in order to compute this kind of partition function, for example, is you take your graph, you pick a root, you arrange it, and then from the leaves, you pass the message from the variable to the factor, from the factor to the variable, from the variable to the factor, until you reach the root node. So it's basically traversing a tree. Once this has happened, so all the messages have reached the root, you can read off the partition function there. And it turns out not just that, but you can also extract other information from these messages. So, for example, if you want the message, or if you want the probability that one specific variable has a certain probability, so the marginal probability at one of the variables, that's just proportional to all the incoming messages. So you would, well, in order to do that, you would send the messages up and down. Well, you can look it up, sorry. But you would get all the incoming messages to your variable, multiply them up, and then you get something which is proportional to the actual probability. So you still need to normalize it, but now this is there's just one unknown value, right? It's the state of yi. So you can normalize it by summing over all values of y. That's just summing the entries of a vector. That is not inefficient. Yes.
So the problem becomes much easier if we don't need to calculate that, right?
Yes.
But in many practical situations, I think we don't need to calculate because who cares if all the probabilities sum up to 1? If we need to just compare two states and which one is more likely, then
yes, but right, if you only want to say which is the highest state, you don't need the partition function. That's one of the arguments of the next. So this is computing probabilities, right? You want to say the probability of the arm being here is 0.5, the probability of there is 0.1. And maybe you want to make a decision based on that, and then you need to know if your probability is 0.05 and 0.01, or if it's 0.5 and 0.1. So there's a situation where you do need the real probabilities, yes. There's a few situations where you don't. So if you only look at the one configuration that has the highest probability, you don't. I mean, going back to the decision before, if your loss is 0.1 loss, then the best prediction is to use the configuration of maximum score. That doesn't need the partition function. But the other one, the Hamming loss, you actually had to decide based on the marginal probability of each label, and that you would have to compute. Yeah, you need to compute it locally, right? You have to integrate out all the others. It depends on the situation. Okay, so this is a very, very, very famous algorithm. It's a so-called belief propagation or sum product version of belief propagation. It shows up in many, I mean, it has been developed many times. You can also just call it dynamic programming. There's a different variant of that is not the sum product, but the max sum algorithm, which doesn't compute the sum over all states, but the maximum over all states. We'll see that next time. In this view of like sending messages from variables to other variables, it's not the most intuitive concept in the world. I agree, but it's an extremely useful algorithm. And the best thing is it computes exactly the right quantities. So there's no approximation involved. Even for an extremely big graph to start with, it will still compute the right, exactly right values in a very efficient way. All you need to do is matrix vector multiplications for a couple of times. And if you cannot do that, usually you don't want to use such a structured model anyway. So for example, for this pose estimation thing, the model you did is you have this kind of tree structure, right? It's a body with arms and legs. You can again forget the x, which is fixed anyway and doesn't enter into our computation. So it's a tree-structured model for pose estimation, and belief propagation is the best and most efficient way for computing any kind of quantities on these kind of models. So it's the state of the art and has been forever. So for example, using this, you can make predictions about body parts, and the typical thing to do that would be, if you want to know where the arm is, then you want to know, well, the distribution of arm locations given the image. And if you do that without any kind of constraints between the body parts, you get very blurry things. So this visualization should show you blue is what's the likely location or the likelihood of the head being here. This is the shoulder being here. This, I guess, is the torso and so on. And if you do introduce these pose constraints, and then you compute still the marginal probabilities, so just the probability of one body part at a certain location, but taking into account all the others potentially, you will get a much nicer picture where the localization is much better. So it found out that it cannot put any body parts here because that would make the connections bad and so on. So these marginals are a useful way of characterizing the uncertainty of your model. And you will need them later for learning as well. There's some problems with belief propagation. I showed it to you for chains. I showed it to you for trees. And that's the only ones that work. So if your distribution is not given by a tree structured model, then you cannot use belief propagation in this easy form. Why not? Very simple. You need a root and you need leaves. If you don't have a tree, there is no root and no leaves. Or at least nothing consistent. The other thing that it doesn't handle in this obvious case is if you have factors that have more than two variables at a time. So if you have a model with one factor that has 3 inputs, the algorithm you saw before is also not going to compute the right thing. It's only if you have like variables on a tree with exactly factors of size 1 or 2 in between. So is all hope lost? Sometimes it is, sometimes it isn't. Sometimes you can actually get away with this because you still have the freedom to choose a parameterization of your model. So what you call a random variable is up to you. So sometimes you can do a trick. So if you have a model with a loop, maybe each of these is a binary variable. You can just collapse it and call it a big variable with 8 possible states. So if you combine these 3 into one with the product of states, then you have like a giant super variable here connected to regular variables there. You just forget that it has an inner structure. It just has 8 possible values. And you have a chain, and you can run the belief propagation. So if you have just a few little cycles, you can often collapse them, and still you're good, and you can run belief propagation. Similarly here, you have a factor of higher order. Belief propagation doesn't like that. But if you collapse these 3, then you don't have any factor at all anymore at that location. So you just have one big random variable, and two other ones, you forget the inner structure, which should, by the way, look different, should look like that. And you run your belief propagation. So this is a general recipe. If you have something that doesn't follow this tree structure, you can sometimes use your graph and convert it into something that has a tree structure, but you will need to change the nodes of the graph into something combining multiple random variables. In fact, there is a general algorithm for that. It's the so-called Junction Tree algorithm. It's also very famous in graph theory. I'm not going to explain it, but it's in the textbook of graph algorithms. So what can you do? If you have a graph with loops and all kind of stuff that you don't like, yes?
How much information do you lose?
You don't lose any information. No, you don't lose any information. This guy has 8 states, or for example, this guy has 8 states, right? And you compute a value based on 8 possible values for all possible configurations. This guy is in a new random variable with 8 possible configurations. You can assign it exactly the same values as before. What you lose is not in terms of accuracy. You would compute exactly the same thing. You lose in terms of efficiency, as we'll see in a second. So the junction tree is the general recipe for that. Take an arbitrary graph, turn it into a tree graph where each node of the graph might consist of multiple of the original random variables. So it started with A, B, C, D, E, F, G. This is the corresponding junction tree where now you have a super node here which has actually these 3 together, another node here. So if this had 10 states and this had 10 states and this had 10 states, then this now has 1,000 states. And it has some connection to the next super variables which also has 1,000 states. So this is always possible. You can always take any graph and turn it into a tree. And in fact, there's a quantity called tree width that will tell you how bad this merging actually be and how much you lose. The problem is the state space of these supernodes will grow. The more you have to merge, the more it grows. And if you have a complex graph where you have to merge a lot of things into one, then you will just not be able to store you cannot execute your matrix multiplications anymore. Right? So in here, you would have a 1,000-dimensional variable instead of 3 10-dimensionals. So in order to send a message from here to there, you have to do a matrix vector multiplication of a 1,000 by 1,000 matrix with a 1,000-dimensional vector. That you can still do. If it happened to be a 1,000,000 by 1,000,000 dimensional matrix, you might be lost and you cannot do it anymore. So in some rare cases, the models are still doable with a junction tree. In practice, usually it gets too inefficient too quickly. So for example, if you have an n by n grid, that's clearly not a tree, but you can turn it into a tree where you have basically length n, and each variable has size n, n of the original variables. And that is typically too much. So belief propagation will get inefficient, even though in practice in theory it's still an algorithm. Okay, I promised to stop 5 minutes early last time, so I will stop 5 minutes early. Thank you.